In our quest to study the notion of continuity in its most general setting possible, we have already gone over from our starting point, which was functions on a real line, to metric spaces and continuity of functions between metric spaces. In today's lecture, we are going to take the next step. We are going to talk about topological spaces and how to define continuity of functions in spaces where there may not even be a distance function. But before we go there, let us take a look at exactly what we have learned so far about metric spaces. Let me just remind you that a metric space is a ordered pair m, d, where m is a set and d is a binary function on that set. It takes two elements of m and maps them onto a real number. Of course, any arbitrary function which maps two elements of m to a real number will not do here. This particular function has to satisfy certain properties if it is to be acceptable as a metric function. And these properties are rather simple and they have been listed out on your screen right now. For any two elements x and y of m, d of xy must be the same as d of y, x, which squares with our standard conventional notion of distance. Also, the distance between 2 points has to be a non-negative number, and it is 0 if and only if the 2 points are identical. Finally, we have the third very important property of a distance, the so-called triangle inequality. D of xy plus d of yz is always larger than or equal to d of xz for any 3 points x, y, and z of m. This is called the triangle inequality for the simple reason that this is a generalization of our standard Euclidean geometry result that the sum of two sides of a triangle is always larger than or equal to the third side. Note that on the real line, the modulus function has all the necessary properties of the distance function d. Indeed, the distance function d has been modeled on the modulus function. But now that we have a setting, a more general setting than the real line, where we can talk about distances between points, we can immediately talk about how to define continuity of a function between two such spaces. So, if m1 and d1 and m2 and d2 are two metric spaces, then the function f, which maps m1 into m2, is continuous at a point a belonging to m1 if the following condition holds. You would realize that this is really nothing but a direct generalization of the condition of continuity on a real line. For all epsilon greater than 0, there exists delta, which is greater than 0, such that the distance d1 between the points x and a being less than delta will imply the distance d2 between fx and fa will be less than epsilon. Or in other words, we can keep the function f of x as close to f of a as we want by choosing a sufficiently small value of epsilon, simply by confining x to a very small interval of points close to a. Now, this interval, of course, is something that we use on the real line. On a general metric space, we have this generalization called the open ball. And in the language of open balls, the definition of continuity simply becomes, for every epsilon which is positive, there must exist a delta which is positive, such that the open ball of radius delta centered around x, according to the metric d1, maps under f to a set which is contained entirely within the open ball of center f of x with radius epsilon. Of course, this open ball has to be according to the metric d2. And just to remind you, the open ball here is a direct generalization of the notion of the interval on the real line. B centered at x, radius r, according to the metric d, is simply the collection of all points y in your metric space such that the distance between y and x is less than r. The name ball, of course, comes directly from the case where we use ordinary three-dimensional space and Euclidean distance, standard notion of distance, as the distance metric. Now, by defining continuity in a language which uses open balls, we have already taken our first step in moving away from the confines of distance function. However, the open balls, of course, very much contain the notion of distance because they're defined via the distance function. In order to go further, we will have to introduce the notion of something called open sets. Now, open sets on metric spaces are defined concepts. You define them simply by demanding that a subset U of M is open if all its points are interior points. In other words, if for every point x belonging to U, there exists some non-zero radius, positive radius r, such that the open ball of radius r centered around x is entirely contained within U. This last thing is what you mean when you say the point x is an interior point. What we are demanding here is that all points are interior points, so that for every point in an open set, you can place an open ball centered around that point entirely within that open set. Now, while this definition of an open set on a metric space depends ultimately on the notion of open balls and hence on the notion of distance, you will see in this lecture that it is possible to define open sets without reference to distances at all. And that actually will be the step that we will need to take to go on to the most general setting for continuity. But before we go there, the task that we need to complete is to rewrite the definition of continuity entirely in the language of open sets, so that once we have a notion of open sets without this notion of distance, we can talk about continuity, even going beyond situations where we cannot talk about distances. In other words, our aim is to free ourselves from the shackles of the distance function while talking about continuity. And that is exactly what is going to lead us to the notion of topological spaces. But before we can do that, we need to rewrite continuity in the language of open sets. And that is what we are going to do next. The first thing we will do is state and prove a theorem, which essentially is a redefinition of continuity in metric spaces using the language of open sets. A function f from a metric space M1 to another metric space M2 is continuous at a point A belonging to M1 if and only if for every open set V in M2 which contains f of A, there exists an open set U containing A such that f of U is contained within V. In other words, U under the action of f maps entirely inside V. Now, this notion of an open set containing a point recurs over and over again in discussions of this kind, and because it's a bit awkward to keep on saying that, there is an alternative nomenclature for this. We often say, instead of V is an open set containing f of A, simply V is a neighborhood of f of A. And using the language of neighborhoods, this theorem reads, a function f from M1 to M2 is continuous at A belonging to M1 if and only for every neighborhood V containing f of A, there exists a neighborhood U containing A which maps entirely inside V under the action of f. Now, this is not a definition of continuity at this point because we already have a definition of continuity. If we are going to treat this as a definition of continuity in metric spaces, we must show that this is actually equivalent to the previous definitions that we have stated a while ago. And that is exactly what we are going to prove now. In the first part of the proof, we are going to assume f is continuous. In other words, we are going to assume that f defines the epsilon-delta definition of continuity that we have already stated. Now, we start with V, which is an open set containing Fa, a neighborhood of Fa. Since every point in an open set is an interior point, Fa has to be an interior point of V, and therefore there must exist a positive number, epsilon, such that the ball of radius epsilon centered at Fa must be contained entirely within V. Of course, this ball has to be defined using the metric on M2, that is the metric D2. And this is nothing but the definition of what an interior point is. Remember, an interior point is a point around which you can put a ball which is entirely inside your set. Now, for every epsilon which is positive, there must exist a positive delta. This is from the definition of continuity that we had written down before, such that a ball of radius delta centered at A, according of course to the metric D1, will map entirely inside this ball of radius epsilon centered at Fa. This is nothing but our epsilon delta definition of continuity written in the language of open balls. But remember, this thing is contained entirely inside V. In other words, we have an open set, namely this ball of radius delta centered around A, which maps entirely into V. F acting on that is a subset of V. And this is, of course, what you demand in the theorem. There has to exist an open set containing A, which maps under F entirely into this open set V containing Fa. And since this is an open set, something we had proven in the last lecture, what we have managed to do is construct exactly one such open set. Remember, this may not be the only open set containing A which maps inside V. In fact, usually there will be infinitely many more. But as far as the theorem is concerned, we need to show the existence of at least one such open set, and that's exactly what we have done. So if F is continuous according to the epsilon delta definition, then F is continuous at A according to this theorem. But in order to show that the statement in this theorem is an equivalent definition of continuity at A, in other words, the statement is completely equivalent to the epsilon delta definition of continuity, we need also to be able to show the converse. In other words, if F satisfies the conditions in this theorem, given any neighborhood V of f of A, there must exist an open neighborhood U containing A which maps entirely into V. We have to show that the epsilon delta definition of continuity will also follow. To see this, we start with a positive epsilon and note that this open ball of radius epsilon centered around f of A is definitely an open set containing f of A. So if the conditions of our theorem are valid, then there must exist an open set U belonging to M1 which contains A such that F applied on U will take you entirely inside this open ball, which after all is an open set containing f of A. Now because U is open, every point in U, in particular the point A, has to be an interior point. Therefore there must exist a positive delta such that a ball of radius delta centered around A must be contained within U. This ball of course has to be a ball according to the metric D1. So if you apply F to this open ball of radius delta centered around A, the result of course will be contained within what you get when you apply F on the entire open set U. But f of U, we have already seen, is contained entirely within this open ball according to the conditions of our theorem. So if the conditions of our theorem holds, then for every positive epsilon, you will be able to find a positive delta such that the delta ball centered around A will map under F to something which is entirely inside an epsilon ball centered at Fa, which exactly is our epsilon delta definition of continuity stated in the language of open balls. What we have shown here is that our theorem is exactly equivalent to the epsilon delta definition of continuity, and we can actually use this definition instead of the more traditional epsilon delta definition. The advantage? This definition is entirely in the language of open sets. And this is going to be the tool which will help us to move into a setting where we can talk about continuity without worrying about distances. In fact, the definition of continuity becomes even more simple in the language of open sets if instead of talking about continuity at a point, we talk about a function which is continuous everywhere. A function f from a metric space M1 to another M2 is called continuous if it is continuous at all A belonging to M1. In other words, if you just say that a function is continuous without specifying where it is continuous at, then you mean that it is continuous everywhere. Now, for such continuous functions, we have a theorem which allows us to state or give an equivalent definition of continuity. A function f from M1 to M2 is continuous if for every open set V on M2, f inverse V is open in M1. So a continuous function is simply one which maps, or rather inverse maps, open sets to open sets. Let me just remind you that f inverse V is by definition the collection of all points which mapped into V. This is a set which is well defined even if the function f is not invertible. Now, on metric spaces, this is a theorem. Once again, it's a theorem because you can prove it by starting from the definition of continuity that we had already stated in the epsilon-delta language. So, to prove this, let us start with the demand that if f inverse V is open for all open sets V, in this case, we will start with a specific open set. The open set, which is an open ball of radius epsilon centered at Fa. F inverse of that will of course also be open. Now, one point which this set definitely contains is the point A, because A will definitely map into the center Fa of this particular ball. Now, because this set is open by our statement of the theorem, then A, a point in the set, has to be an interior point. And therefore, there must exist a positive delta such that a ball of radius delta centered at A must be entirely within this set, F inverse B Fa epsilon. Or in other words, if I apply the function f on this particular open ball, what I'm definitely going to get are elements which are all inside this epsilon ball centered at Fa. This, notice, is exactly our definition of continuity in the epsilon-delta language stated in terms of open balls. So, if a function is continuous according to the definition stated in this theorem, it is continuous according to the epsilon-delta definition. But we need to also show that the converse is true to prove that these two are equivalent ways of saying the same thing. So, let us now start by assuming that the function is continuous according to the epsilon-delta definition. In other words, for every point A belonging to M1, remember, continuous means continuous at every point, and every positive epsilon, there must exist a positive delta such that the delta ball centered around A must map under F entirely within the epsilon ball centered around Fa. We are starting from this, and we will prove that this will imply that the inverse image of every open set on M2 is going to be an open set in M1. So let's start with V, which is an open set in M2. Now, if F inverse V is null, that's always possible. That is, there are no elements of M1 which map onto the elements of V. Then the statement that F inverse V is open is trivially true. Remember, the only way in which a set can fail to be an open set is that it contains points which are not interior points. But since the null set contains no points, it simply cannot ever disobey the conditions which make a set open. We usually call this kind of statement vacuously true. So the interesting case is when F inverse V is not a null set. In other words, there must be at least one element A which belongs to F inverse V. In other words, there must be at least one A such that F of A belongs to V. Now V, remember, is an open set. So V is an open set which contains Fa under these conditions. So Fa has to be an interior point, so there must exist a positive epsilon such that the epsilon ball centered around Fa must be contained entirely within V. I'm not going to keep on mentioning which metric the ball is going to follow because that should be clear from the context. Now, because the epsilon-delta definition is assumed to be in force, for any such positive epsilon, there has to be a positive delta which ensures that the delta ball centered around A maps under F entirely within the epsilon ball centered around Fa. But this, in turn, according to our statement just now, is contained within V. This delta ball must map within V, and so the delta ball must be contained inside F inverse V. Because for any point A belonging to F inverse V, you have this result that you can find the delta ball centered around A, which is inside F inverse V. It shows that every point of F inverse V is actually an interior point. And that is exactly what we mean when we say a set is open. So what we have managed to prove is that if the epsilon delta definition of continuity is in force, then for every open set V in M2, F inverse V is an open set in M1. We have shown that the equivalence actually works both ways. Instead of using our epsilon delta definition of continuity, we can just as well use this definition of continuity. A function is continuous whenever the inverse image of every open set is an open set. Now the reason why these theorems, which are after all equivalent definitions of continuity, turn out to be so important for us is the following. As far as continuity of maps on metric spaces is concerned, the precise details of the metric functions, as it turns out, does not matter. What matters is which subsets are open. If you know which subsets are open, you can decide whether a function is continuous or not. So, the collection of all open sets is what decides continuity of a given function. In a metric space, the collection of open sets is defined via our definition of an open set being a set which contains all its interior points and only its interior points. And this collection goes by the name of the metric topology for this particular metric space. And the important thing that we have already seen in the last lecture is the following. Equivalent metrics on a set M leads to the same collection of open sets, the same metric topology. And as we have already seen, if you replace a metric by an equivalent metric, the same functions stay continuous. So as far as continuity is concerned, you don't really have to look at the details of the metric. All equivalent metrics do just the same job, and it is much easier and much more elegant if instead of getting lost in the details of the metric function, you just worry about the open sets or the metric topology. Given how important open sets are to the notion of continuity in metric spaces, it stands to reason that the next step that we should take should be to try to talk about defining open sets without having to resort to the notion of metrics. So we will talk about a collection of subsets of a space which we will together call a topology, and these elements are going to be our open sets. And we are going to define continuity entirely in the language which involves these open sets. Before we do that, we still must take a look at our open sets on metric spaces to figure out which properties of open sets on metric spaces are really important, the ones which we must still retain in our new defined collection of open sets. So let us now turn to some very basic and important properties of open sets on metric spaces. These properties are things we can prove from the definition of open sets in metric spaces, but later on when we go on to talk about continuity without bothering about distances, we will actually demand these properties as defining properties for our collection, or defining properties for what a topology really is. So if you recall the definition of a topological space that we had stated in our very first lecture, it should be very easy for you to recognize why we need to prove the next couple of results. The first result that we will prove involves the intersection of open sets in metric spaces. The theorem is the following. If u1, u2 up to un are open sets in a metric space M, D, then so is their intersection. In order to show that, we need to show that every point in the intersection is an interior point. So let us focus on one such point. If x is an element of this intersection of u1, u2 up to un, then for every one of the I values from 1, 2 up to n, x must belong to ui. In other words, x belongs to u1, u2, u3, u4 all the way up to un, all of them. And since x belongs to ui, this implies that x is an interior point of ui, and therefore there must exist a positive number ri such that an ri ball, a ball of radius ri, centered at x, must be contained entirely within ui. So we have one such R for each of the n open sets that we are talking about. The next step would be to look at the minimum of all these Ri's. And this R, which is the minimum of a lot of positive numbers, must be a positive number itself. And so we can take R as the radius of an open ball centered around X. But since this radius R is less than or equal to each one of the Ri's here, it follows that for every I, this open ball of radius R centered around X is contained entirely within the open ball of radius Ri centered around X, which in turn is contained entirely within Ui. In other words, this particular ball is within each and every one of Ui's. So it must be a subset of the intersection of all the Ui's. And therefore we get this very important result that the finite intersection of open sets is open. The operative word, the very important word here is finite. Note that when we stated that these are open sets, we stated explicitly that you have a finite number of them, a number n. And the reason why that is very important can be seen here. The R, the radius of the final open ball, which proves that X is an interior point to the intersection, is a minimum of R1, R2 up to Rn. Now each of the Ri's are definitely positive. And if you have a finite number of Ri's, then the minimum definitely is guaranteed to be a positive number. If on the other hand, you had an infinite number of different Ri's, so you were trying to talk about an intersection of an infinite number of open sets, then you may no longer be in a position to talk about the minimum of such a set. You can have an infimum of an infinite set, but not all infinite sets have minima. And the infimum of an infinite bunch of positive numbers can very well be non-positive. To see an example, just look at the numbers 1, half, 1/3, 1/4, 1/5 and so on. 0 is not a number in this set, but 0 is definitely the infimum of this set. This set has no minimum, it does have an infimum, but it's not positive. So if you were to try to use this proof in a situation where you have an infinite number of open sets, the stumbling point could be here. You will have to talk about the minimum of R1, R2 all the way up to R infinity, and such a minimum may not exist. The infimum, which will exist because the set is bounded below, all the numbers are non-negative, can turn out to be 0, in which case you can no longer have an open ball of radius r centered around x. Remember, for open balls, the radius has to be a positive number. So this was our first theorem. This theorem concerned the intersection of open sets. The next one concerns unions. For this, we start with any collection of open sets in a metric space M, D, and note that we have not stated whether this collection is finite or infinite. We demand, at least the theorem demands, that the union of any such collection is an open set. Of course, to prove that this union is open, we need to show that every point which belongs to the union is an interior point of the union. So if x belongs to this union, there must be at least one specific index j for which x must belong to uj. That's the definition of what a union is. And therefore, x being an element of this open set uj must be an interior element, and therefore there has to be a positive r such that a ball of radius r centered at x must be contained entirely within uj. But this ball will then be contained definitely within the union of all the ui's, which contains uj as an element. So, for any point x in the union, you will be able to find some r such that the r ball centered at x is entirely within the union. In other words, x is an interior point of the union, and since this is a statement which is true for every point x in the union, every point is an interior point, so an arbitrary union of open sets is open. Note that here we no longer demand finiteness, because here all you require is x belongs to one of the open sets involved, and therefore we just use one r in this proof, not the minimum of a whole bunch of r's. So the problem that you could have with an infinite intersection of open sets is not a problem here at all. So to summarize, finite intersections of open sets is open, arbitrary union of open sets is open. Now, if you remember your topological space definition, you would realize that these are exactly the properties that we define for the collection of sets that we are going to call a topology. In addition to that, we have one more demand in topologies, which is the null set phi and the full set M are open. These are trivial to prove in metric spaces. Note that while these results are things we have proven in the context of a metric space, when you talk about topological spaces, you no longer prove these results. None of these results about finite intersections, arbitrary unions, and the null set or the full set being open sets have to be proven, because they are exactly what goes into the definition of a topological space. To get this topological space, which is the general stage for continuity, what we do is we just define a collection of open sets. Let me just remind you of what we talked about in our very first lecture. A topological space x, t is a set x with a collection t of subsets of x with the following properties. The null set and x is in the collection t, finite intersection of elements of t is in t, arbitrary union of elements of t is in t. And these elements of t are exactly what we call open sets. So what where defined concepts in terms of more elementary ones in metric spaces become the central concepts or preliminary concepts in the context of topology. Now that we have done all the hard work in defining a stage for continuity, the next obvious step would be to define continuity in this context, in the context of topological spaces. And the definition is pretty straightforward and obvious given what we have gone through over the last few minutes. Given two topological spaces x1 t1 and x2 t2, a function f from x1 to x2 is continuous. Now this is a definition. If for all v belonging to t2, f inverse v belongs to t1. And remember, elements of T2 are open sets in the second topological space and elements of T1 are open sets in the first topological space. So this statement can be succinctly summarized in saying a function f from x1 to x2 is continuous if the inverse image of all open sets is open. Note that this is a statement which can no longer be proven in the general topological context. Because in the general topological context, this is exactly what we define continuity to be. There is no other definition from which we can derive this. Of course, the reason why we define continuity in this way is that this is an obvious generalization of the result that we had proven for metric spaces. In a metric space, you can prove that the inverse image of every open set is open. But there, of course, the open sets were defined using the metric, ultimately, and we showed that this definition of continuity was actually equivalent to the epsilon-delta definition of the continuity using metric functions. But now that we have managed to define open sets just as preliminary entities without having to resort to anything else, we can now talk about continuity directly. And this now becomes the basic definition of continuity, not something that you can prove from a more elementary definition. In the coming lectures, we are going to take a look at the properties of topological spaces in some more detail. But before we go there, and before we wrap up today's lecture, I want to address a couple of issues which might be troubling some of you. At least these issues used to trouble me when I first learned about these things. The first issue which I'm going to talk about is why do we have to talk about inverse images? Wouldn't it be much more natural to talk about a function as continuous if for all open sets in the domain, the image of those sets were open in the range? In other words, if u belong to T1, the topology of your domain, then f of u would belong to T2, the topology of your range. Can't we define a function to be continuous if this happens? The answer is this would actually run contrary with the notion of continuity that we have already developed earlier. Especially in the example that we are going to just see, we will see that a demand that a function is continuous if it maps open sets to open sets is actually inconsistent with continuity on a real line. And one example is all that will suffice to show you that this is true. Consider a function, a very familiar function, modulus of x. Now this is a continuous function. It's a continuous function according to the epsilon-delta definition applied to functions on a real line. It's also continuous according to the obvious common sense notion that you can draw the graph of this function without ever lifting pen from paper. So this is definitely continuous. But if you look at what happens to the interval minus 1, 1 in the domain under the action of f, you will see that the result is going to be this interval, which is the interval which goes almost all the way up to 1 but does not include 1. Remember, the domain doesn't have 1 in it. This is an open interval. The endpoints are outside. So neither will the image. The image will not have 1 here. But on the other side, the image will have all numbers which are smaller than 1 and non-negative. In other words, 0 will of course be part of f acting on minus 1, 1. So f acting on minus 1, 1 gives us this interval 0, 1 which contains the point 0. Now it's easy to see that 0 is not an interior point of this interval. If you consider the point 0, any small open set around this, any ball around this point 0 will go outside this set 0, 1, because it will have to contain negative numbers as well. 0 actually is a boundary point of this interval. It's not an interior point. As a result, what we end up with is this example where the image of the open set -1 to 1 is not an open set. So if you want to keep on continuing to call familiar continuous functions like the modulus of x as continuous, then you cannot use the more obvious sounding definition that a continuous function is one which maps open sets into open sets. It simply will not fit what we already know about continuity. Just to see that our definition is not going wrong anywhere, look at the open interval -1 to 1 in the range, the open set V. What about f inverse V? Which points of the x-axis actually map inside this interval? It's pretty easy to see that that is this interval. All points here map inside -1 to 1 open interval. Of course, there are no points which actually go and map here, but when you look at the inverse image, all you do is take every point here and look at all the inverse images of the points and collect them together. So a point which doesn't have an inverse image, which does not come from any value of x, is simply not going to contribute to this. So the inverse image of the open set -1, 1 is actually the open set -1 to 1 once again, which is perfectly consistent with our definition of continuity. You can easily check that every open set in the domain here does not necessarily map onto an open set. We have already given you one example. But every open set in the range has an inverse image, which is an open set. The other concern that I want to address next is simply this. We have started from the real line, generalize that to metric spaces by invoking the notion of distance on an arbitrary set. We already have plenty of examples of metric spaces which are not the real line. So this is a true generalization. Now what we have done here is we have taken the properties of open sets from metric spaces and defined a topological space using this. But are we so sure that this is a generalization? In other words, could it also perhaps be that once we have demanded all these properties from our open sets, the only open sets that we can get are the ones we would get from a metric space anyway? Is it possible to have a topological space which is not a metric space? Now, to see that that is actually true, that you can have topological spaces which are not metric spaces, or in the jargon, you can have topological spaces which are not metrizable, we now invoke a very, very important property of metric spaces, or rather the topology which comes from metric spaces. Every metric topology, the collection of open sets according to the metric space definition, has to have something called the Hausdorff property. What does this say? It actually says that if x and y are points in M and they are distinct points, then there must exist open sets U and V in M, such that x belongs to U and y belongs to V. So you have open sets which house x and y separately, respectively, and these open sets are themselves disjoint. This is very, very important. Of course, the Hausdorff property is named after Hausdorff, the mathematician, but a rather common mathematician's pun here is to say that the Hausdorff property demands that any two distinct points in the metric space can be housed off in disjoint open sets. Of course, this is a property of metric topologies. In other words, This is a property that we should be able to derive starting from the definition of open sets in metric spaces. And the way we do this is very simple. We start from the fact that if x and y are different points in a metric space, then the distance must be positive, and we just halve the distance and take that to be the number r. The reason why we do this is that a simple picture drawn using D2, the Euclidean metric on a plane, as our prototype would convince you that if you took two open balls centered at 2 points x and y with radius which is half the distance between them, then these two open balls will definitely be disjoint sets and they would house x and y separately. Now, there is something which follows on a plane using ordinary Euclidean metric from elementary geometry. But it is easy to see that this will follow no matter which metric space you use. Of course, BDXR and BDYR are balls which are centered at x and y respectively, and they definitely contain x and y. After all, the point x is definitely at a distance which is less than r from the point x. It is at a distance 0. Now, to show that these two open balls are disjoint, what we do is we proceed by contradiction, the standard mathematician's trick. We assume that they are not disjoint, so if this intersection is not null, there must exist some point z in your metric space which is in that intersection. But then, because z belongs to this intersection, it has to belong to both this and this, these two open balls. The distance of z from x must be less than r, so must the distance from z from y be. But these two things together tell you that distance between x and y must be less than or equal to distance between x and z plus distance between y and z. This, of course, is the triangle inequality. Both of these are less than r, so this must be less than r plus r equals 2r. And this, of course, is d of xy. So we end up with a statement that d of xy has to be less than d of xy, which of course is a contradiction. So, on a metric space, you will definitely find open balls which contain two distinct points which are disjoint, and therefore, because open balls are open sets, every metric space is a Hausdorff space. Now, what I was talking about originally was whether or not there are topological spaces which do not follow from a metric. The reason why I have invoked this notion of the Hausdorff property in this discussion is simply the statement that every metric space has to have the Hausdorff property and all topological spaces are not Hausdorff. Therefore, there has to be topological spaces which are not metric spaces. By the way, this is not to say that all Hausdorff topological spaces, all topological spaces in which you can find open sets containing distinct points which are disjoint from each other, are necessarily metric spaces. All we are saying is a metric space is necessarily Hausdorff, and there are topological spaces which are not, so there are topological spaces which are not metric spaces. We can think of plenty of examples of this, but I am going to just give you the simplest one of them all. The simplest topology that is possible, the simplest collection of subsets of a particular set X, which is consistent with all the properties that we have listed as demands for a topology, is simply the set which has only two elements, the null set and X itself. Can easily check that this actually satisfies all the demands of a topology. And this is in fact the smallest topology that can be there on any given set. Smallest in the sense of having the least number of elements. Now, the only open set containing X and Y, two elements of capital X, is capital X itself. Capital X is definitely not disjoint from itself. So you cannot find disjoint open sets which contain two distinct points x and y here. So any situation where capital X has more than one element, so that you can talk about two distinct elements x and y, and you're using this particular topology, which is a valid topology, is one in which the Hausdorff property will fail. And therefore, this topology is definitely not metrizable. In other words, when we have gone on to topological spaces from metric spaces, we have genuinely generalized things. We now have more examples to talk about. All the metric spaces, of course, are topological spaces because they have the metric topology, which satisfies all the basic properties. But you do have other examples of spaces where you either do not have a distance or you may not even want to talk about a distance, but yet you can talk about functions being continuous or not continuous between such spaces. This is, of course, what topology is good for. And we are going to take a look at what consequences these definitions have in the next few lectures.